During the 20th century, the Apollo missions touched down on the Moon's flat, equatorial plains. They aimed for high noon, using the harsh, direct sunlight to easily spot hazards out the window during their brief stays. But to stay longer, we need to extract local resources. That logistical requirement forces the Artemis program to abandon the safety of the equator and target the lunar South Pole. Because of the Moon's axial tilt relative to the ecliptic, the Sun down here perpetually hovers right near the horizon. This specific geometry creates a dark landscape defined by long, sweeping shadows that completely mask a highly rugged and treacherous terrain. Inside the deepest craters are permanently shadowed regions, or PSRs. Without an atmosphere to move heat around, the lack of sunlight for billions of years has turned these craters into thermal traps. Temperatures here plummet to -250 degrees Celsius, colder than the surface of Pluto. To harvest the resources locked in those traps, we have to move past short sunny visits and engineer systems capable of operating in the coldest, darkest environment in the inner solar system. Getting to those resources means dropping a multi-ton spacecraft, like the Human Landing System Starship, directly into that pitch-black environment. Without the visual cues that guided Apollo, astronauts in automated systems are flying blind. They cannot look out the window to verify if their target zone is safe. If the spacecraft touches down on a slope greater than 8 degrees, or a single landing leg strikes a hidden boulder, the structure will buckle. To survive, the lander creates a digital representation of the terrain, adjusting its trajectory milliseconds before touchdown. The success of Artemis 3 and any subsequent expansion on the Moon relies entirely on our ability to engineer a way to see through absolute darkness. NASA's solution is the SPLC project, an advanced navigation suite built around the Hazard Detection LiDAR, or HDL. Instead of slowly sweeping a single laser back and forth, modern HDL uses flash technology. It fires a complete array of lasers all at once, freezing the scene below and eliminating the motion blur that occurs during a high-speed descent. The HDL captures incredibly dense data, pulling in 16 million elevation points in a 2-second window. This yields a terrain map with a 10-centimeter resolution. From 1.5 kilometers up, the computers clearly identify a rock as small as 15 centimeters across. That LiDAR mesh is then layered with real-time thermal imaging. Because solid rock retains heat differently than loose, insulating lunar dust, the system can spot structural hazards buried just beneath the surface. By fusing all these active sensors, the spacecraft turns a dangerous blind descent into a surgically precise touchdown. Pace quickens slightly. Once on the surface, the crew's primary objective is to locate and map deposits of lunar water ice, often referred to as blue gold. But the astronauts aren't looking for shiny sheets of ice. Instead, their instruments are specifically hunting for hydrogen atoms trapped beneath the regolith. When galactic cosmic rays strike the lunar soil, they release fast-moving neutrons. As these travel underground, they collide with hidden hydrogen atoms, slowing down. By measuring these moderated neutrons, the spectrometer creates a depth map, revealing ice concentrations up to 1 meter below. Extracting that raw ice yields a dirty mixture of water, methane, and ammonia. Through in-situ resource utilization, systems like Icicle and IHOP use freeze distillation and rigorous filtration to process and purify the volatile mixture. The purified water is then run through an electrolyzer, splitting the H2O. This provides breathable oxygen for the crew, while the hydrogen, along with imported carbon, is converted into liquid methane to fuel the lander's engines. Extracting and refining these resources turns an isolated frozen impact crater into an operational refueling station. All of this data, the high-resolution topography and the mineral mapping, feeds directly into the blueprint for a permanent outpost, Artemis Base Camp. This topographical map of the South Pole shows the extreme contrast in real estate. The deep, permanently shadowed craters in blue hold the ice, while the high-altitude crater rims in yellow, known as peaks of eternal light, receive near-constant solar illumination. Operating here requires a split power strategy. Crews will deploy vertical solar arrays on the sunlit peaks, while lowering nuclear fission surface reactors directly into the shadowed craters to ensure a persistent power grid. The habitats themselves, like the proposed Luna outpost, won't be shipped from Earth. They will be 3D printed on-site by autonomous robots, extruding a composite mixture of lunar regolith and polymer binder. These printed vaults are engineered to handle immense pressure. Once the shell cools in the vacuum of space, it must support nearly 3 meters of loose lunar soil piled on top, which acts as a vital shield against galactic cosmic radiation. The precision navigation required to land safely also maps the foundation for sustainable architecture in an aggressively hostile environment. The Artemis III architecture marks a distinct threshold in our spaceflight capabilities. By laying the groundwork for a permanent outpost, we shift our operational baseline from brief excursions to a sustained multiplanetary presence. The lunar South Pole offers a high-stakes proving ground. It validates closed-loop life support, scales up heavy logistics, and tests long-term partial gravity. Running complex extraction and construction systems just 3 days away from Earth allows us to troubleshoot catastrophic failures before attempting them on a 7-month transit. Mastering the eternal shadows of the Moon is the necessary operational rehearsal before we leave our local system and set foot on Mars.